Hello and welcome to Multivariable Physics. This is going to be episode 2A, so this is going to be just some extra things on vector functions, which are kind of important to remember because I glossed over a few important details. So if you remember really what these vector functions are, okay, they're a function from one vector space to another. Okay, and they're inherently nonlinear. So this is not exactly the same as a matrix. If you're familiar with linear transformations, we have linear transformations from Rn to Rm. That this is not the same. This is a function that, when applied to a vector, is equal to a vector of nonlinear functions. Okay. And blah blah blah. So we're gonna start moving away from just two dimensions, which is what we looked at in the last episode, and we're gonna actually think about the different cases with n and m's. So we have three cases, right? Three cases. Sorry, my handwriting's terrible, but first case, n is greater than m. N is less than or equal, or n is equal to m, and then n is strictly less than m. So I'm going to be moving through this a little quickly, but for the most part, there's not too much. So n equals m, we kind of briefly covered already, but I'm going to look at this one first, okay? Then I'll go back to this guy, and then we'll deal with this guy last. So n is greater than m. What does this tell us? Well, this is simply a parameterization of something in a higher dimensional space. Okay, so we're gonna think in R2. Here's an X. Here's a Y. Oops, I should probably make this full on. And we're gonna think about this function, R of t, which is equal to cosine t sine of t. Okay. What does this look like? Well, you should all be familiar with this. At, well, t equals 0, this is a 1. And then actually I'm going to make this red. T equals 0, this is 1. At r equals pi over 2. So r pi over 2. And then here we have 1. Here's, or equals 0 and 2 pi. And then here's 3 pi over 2. Negative. Which that should be green, but whatever. Right? And here's negative, or is negative pi, or just pi. In this case, it shouldn't be negative. Right? This forms a circle. Right? This this function here, rt equals cosine t sine t, parameterizes a circle in 2D space. Just a single curve. Okay. Now we can think in terms of 3 dimensions. If we were to think of this function, so if we were to modify this, okay, so we had rt cosine t sine of, or v cosine u. That's how I'm going to do this. It's not t, it's going to be r u v, okay, is equal to cosine u sine v sine u sine v cosine v. Right? Now this equation is going to parameterize, if we have 3D space, x, y, and z. This is going to parameterize a sphere. You can go and do the math and check maybe I got one of the parameters wrong, but you can parameterize a sphere in 3D space with this, right? So that's that. Pace. These parameterized space curves, okay, or surfaces, right? Like if with just 2 dimensions, if I'm in 3 dimensions, I could parameterize. If I'm sitting here in 3D, right? Oops, wrong color. I'm sitting here in 3 dimensions, x, y, and z. Well, I could define a function rx, y that parameterizes the entire plane. So that's that. That's the first case, okay? And the second case is gonna be a bit trickier because I'm gonna have to erase a lot of stuff here. But actually, I probably don't need to. I could get away with just writing it here. This n equals 0 case here. This one is what we already looked at. Vector fields. But there's another important thing, which is actually the change of variables. Okay, and in this case doesn't come up that often, but I will briefly talk about it here. So I'm going to split this up into different groups. Some colorful. Actually, I should keep the colors consistent. And then this is going to be, make it pink. And then here's this, and then all this purple stuff is going to be the rest. So what does this look like? So what does change of variables look like? Well, say we have x, y, okay? What I'm doing is I take a function, okay, f of x and y, okay? And I turn this into x cosine y. I turn this into another function of x sine y. Turn this in terms of a function of position into a function of radius and angle, right? Oops, I should probably, right? So we change our variables, or we do a change in our coordinate system. That can be done through a vector function where n is equal to m. Okay, so obviously an example of that, if we have an object, actually an example of both of these, we have some object in space, so here's Earth, right? And we have the moon, and the moon is orbiting the Earth, right? We could use x and y, right? And the function on the moon is going to look something like this, right? fxy. It's going to have gravity, and it's going to look ugly because we have, x squared plus y squared in our bottom piece, gm, whatever, right? We don't want to do this. Instead, we're going to translate this into a better coordinate system. So you're going to have, should probably make this straight with the moon, a radius, and then and then an angle. So we turn this into polar coordinates, right? Change this variable into polar coordinates, and then now we can describe the change in terms of, well, we have the force acting on its radius and the force acting on its rotation, right? And these actually shouldn't be vectors, ignore that. Or actually just yeah, pretend that, right? And so that's how you would describe that. You would use this type of function, okay? you would just change the coordinates up, and then in this case r equals, you would parameterize this r cosine theta, r sine theta, right? That's how you would parameterize x, at your xy turns into this. You'd be able, if you're familiar with change of coordinates, we'll get into that a little later, but that's another option. And then finally, this last one here, n is greater than m. What can we do with n when n is less than m? And the answer is simply conic sections. I don't. So these are a little tricky at first. But one way to think about this is, okay, so we're gonna have a function from r cubed to r squared, and it's gonna look like x squared plus y squared minus z squared, z plus 1. Okay. And what does this look like? Well, what this looks like in 3D, if I'm going to graph this, is, so we have some plane, okay, and then we're going to have some cone, right? And then we're gonna have this circle here parameterized by that. And this is the graph when our vector function f is equal to the 0 vector. Okay. Right, and so you can kind of think of this as like, is equal to 0, 0. That's kind of like the roots of these. Solving it's almost like you're solving a linear system of equations, even though it's non-linear. But this parameterizes it. It's a cone, and you're basically slicing it with some plane. Another example is we could think maybe we slice it vertically. I'm going to change the color again. Sorry. Maybe we slice this vertically, so we end up getting two cones here. So here's here's our conic. We end up slicing it here. That's another way to think about one of these. These don't show up. These probably aren't going to show up too, and the examples are going to be doing, but they're important to keep in mind. And yeah, so I know this is long. I'm thinking of making these go a bit faster. This episode is already like 13 minutes, so I'm thinking of going at a bit of faster pace. But there's also a lot to cover, so I'm not sure how quick I can go. But yeah, thank you for watching.